complex polynomials and simple polynomials. Simple polynomials. Colored complex polynomials, they appeared in Chern-Simons theory. So if we have any knot, there is a three-dimensional theory where we integrate over space of one forms on a three-dimensional manifold with values in every algebra. If we have such one form, then we can integrate it over a knot. So consider Hovanova of A along the knot, and such observable is called Wilson loop. In particular, if we take the group, the algebra G equals to S2, and I forgot to say that we should choose a representation in which we take the Hovanova and take the trace. Then we take average over all H in equivalent classes of connections. So this is physical definition. Yes.
Все эти слова бессодержательные, они попроскакивают, это все мотивировкой служит, потому что настоящее определение совсем другом состоит.
Да, совершенно.
Это те слова, которые все приговаривают в начале доклада, не имеют в виду вкладывать какой-либо смысл.
But the Reshetikhin-Turaev approach can be explained as this calculus in some specific gauge. Okay, let me introduce a representation here, lambda. And then, so we integrate over all connections modular gauge transformations. Then we can choose a gauge if we represent R3 as R2 times one-dimensional space, R1T. Then we can choose a gauge where this connection has zero component equals 0. Then in this gauge, the theory becomes almost free, and so actually we obtain the Reshetikhin-Turaev approach, which is rigorous. So we have a four-valent graph, which is a projection of a knot with two kinds of vertices, this and this, and we associate our matrix of this group in.
А вот сейчас как раз начинается определение. Все до сих пор были размахивания руками, а сейчас начинается настоящее.
Is it about knots or links?
Also about links, but links are much more complicated. I will mainly focus on knots. So we put two kinds of R matrices. We put R here and R inverse here. So knots are oriented. And if we have sort of maximum or minimum, then we put canonical element. This corresponds to representation V, and this is dual, since it is for the opposite representation. And there is a canonical element in V and the V dual. So such a contraction of R matrices is the definition of just identity element. Casimir is element of of S squared of G. This is the representation. Yeah, but it acts, the Casimir acts with by some eigenvalue in the representation. So actually, this is correct. For example, if we have the simplest possible knot, this torus knot T to M, this computation reduces to computation of trace of the R matrix to the power n in the tensor product. These two representations, and R matrix is the intertwining operator for this representation. So we can decompose this as sum of irreducible representations. Actually, here we take gradient trace. It's like a Q trace. There is some grading operator, and our matrix it preserves the grading.
So
R X in any representations of some quantum group, for example, UQ and QGLM. So we associate a representation to a knot. So we have representation of a quantum group. There is actually of
your matrix is a representation of it.
in any representation, and in particular, our matrix actually it acts from any two representations R1 times R2 to R2 times R1. But in this particular case, we choose lambda times lambda. Yes. And then our matrix acts by some eigenvalue in each representation. So for this simple example, it is enough to know just its eigenvalues. And for example, for the fundamental representation, if number is just the defining representation, single box representation, we get a polynomial due to n and capital so in this example, this representation,
Just the thing. For the trivial representation, yes, the value of this quantum invariant on this node,
yes, yes,
so it's not
is this, yes. Each single box of T to N. And
because
yes, then the product of it, it decomposes to sum of two representations. This is this Young diagram plus this Young diagram, as usual, peer review. I forgot to say the notations here. I denote by bracket n the quantum number, and this is q to n over q, where x is x minus x inverse. So these are graded traces, traces where we also weight with respect to the gradient. And these two monomials are eigenvalues of the R matrix in this representation.
what does it mean? Plus and then minus and
This is just a monomial minus q to this point.
the right bracket should be in a different one.
This bracket corresponds to this.
No, it should be moved to the left. minus q to this power.
No, it's always minus because n is odd to have a knot. N should be odd. And eigenvalues of the R matrix here are q and minus q inverse. So we take q to n minus 1 and minus q inverse to n minus 1. So we can find
brackets.
I just additively wrote two contributions, so we can write minus here. Okay. And in general, if we have some not presented as the closure of a break, which is always possible by artist's theory. Not presented as a closure of break. So we have several number of strands. Then we have intersections in any subsequent strands. So we have R12, R23, R matrices, Rn minus 1n. They satisfy Young-Baxter equation, which is R12, for example, R23, R12 equals to R23, R12, R23. And we can always diagonalize R1, but other R matrices don't compute with it, so they are not diagonalizable simultaneously. But there is a very good description of them due to Kirill and Vishetikin. So it is very simple when the representation here is trivial. And I will tell you later how to reduce any representation to the case of trivial, of just defining representation, vector representation. So we have a vector space that is associated with this collection of strands. It's just box 2n. And this is decomposed to sum over Young diagrams, representation lambda, to the power number of standard Young tableau associated with them. So we can construct a graph starting with just a box. Then graph is when we add two representations that are obtained by multiplication by this fundamental representation. So if we multiply this by fundamental, we get these two representations. If we multiply again, we get this, and this. So we get this representation two times. So for example, if we have two strands, the decomposition will be this representation plus this representation twice, plus this representation, and so on. And there is a natural basis in this whole space called the Geffern-Friedman basis.
Что такое R1? What is R1?
This is the operator acting for these two tensor vectors, and I will describe it explicitly how we act. So then we have Differential basis in this representation. It is given by Young diagrams lambda and a standard Young tableau denoted by T. Standard Young tableau is filling this by numbers from 1 to total number of boxes in lambda, so that it is increasing in columns and rows. So, for example, for this diagram, we have two standard Young diagrams. This, right, thank you very much, Young tableau, and this. The slightly more twist is 2. And let's describe how I plus 1 acts in this basis. Let's denote basis element by VT for any Young tableau. Young tableau in particular defines its shape, its Young diagram. So this is so these are matrices are quantizations of the just permutation operators in the symmetric group. They satisfy braid Artin relations. So this has to do with permutation of numbers I and I plus 1 in the Young tableau. So we can take T and apply permutation I plus 1 to the tableau. And this may or may not be a Young tableau. So it may happen that if we apply this permutation to T, the order is not increasing for columns or in rows. So there are two cases. I plus 1. So first, if I plus 1 is not a tableau, Young tableau for the same diagram, then this vector is eigen for this operator I plus 1, and it can be Q times Vt or minus Q inverse times Gt, depending on the following. If this is not a standard Young tableau, it means that I and I plus 1 are in the same row or in the same column. In this case, we put Q, and in this case, we put minus Q inverse.
Sir, what do we commute?
What?
How does the permutation act on T?
This is just some filling by numbers, so we can switch numbers I and I plus 1. So this is the case when the resulting table is not a Young tableau. So, and the second case is if T prime, which is I plus 1. Yes, because it is increasing and something should be between them. So the second case, when this is a Young tableau, it means that I and I plus 1 are not close to each other. Then there is a 2 by 2 block corresponding to this. This is called flip case, and it is the following. So there is M, which is difference of contents of these two blocks, I minus I plus 1, and the 2 by 2 block is minus Q minus Cm, Sm. So it can be chosen in orthogonal form, where Cm is 1 over m, Sm is square root of 1 minus Cm squared. Yes, this is content. Thank you very much. Content of a box is its distance between the diagonal, the main diagonal, and the box, which is sign. Okay, and these are actually quantizations of the formulas of Vershik and Akmikov for representation theory of symmetric groups. When Q is equal to 1, the same formulas were obtained in their paper. So this is completely algorithmic. And if we want to consider now colored representation, so we want our matrix between representations from lambda times mu to mu times lambda by standard fusion procedure, И.Чередника and others. We can invert any representation lambda to representation a single box to the power number of boxes in lambda, and we can then consider our matrix between these products of fundamental representation. Itself, this is our matrix, and restrict it to the subrepresentations. So practically, what
has this R any relationship to?
so
This are matrix exchanges to irreducible representation.
yes, these two arbitrarily irreducible representations, and this just for single box. So and practically, if we want to compute colored Hopf polynomials, we should replace each. So if we want in representation lambda, then we have to replace each strand by the number of boxes in lambda parallel strands. So for example, it will be this is for if there are two boxes, so we get a very big diagram, and we introduce certain projector operator here, which selects just this sub-representation. And this way, one can compute colored complex polynomials, but practically, these are huge matrices. And for fundamental representation, it is possible to do on computer when number of strands is less or equal than 10. So if we want, for example, to compute this in representation to 1, in this representation, then the number of strands should be less or equal than 3. And a lot of interesting nodes cannot be represented as braids with 3 strands. That's why one has to develop some other approaches. Any questions? So suppose we want to compute in the representation 2, 1. This is embedded to the box 2, 3, our 3. That's why we replace each strand in our node by 3 strands. For example, if we started with a node with 3 strands, then we have to do to compute fundamental complex polynomials from 9 strands. That's why colors are very hard to compute.
So it multiplies the number of strands.
Yes, by the number of boxes in the representation. Okay, there is another approach which appear in conformal field theory.
This is just because this is a result of the fusion procedure.
Yes. Conformal field theory. So this was originated by Newton. And it works well for knots, for so-called two-bridge knots. These are knots when we have, at each step we have 4 strands, and they are divided to 2 pairs by 2. And we can make crossing in close strands. Then we can change strands which are closed. For example, we can go here and make any crossings here. Then again here. And then we close like this. So we go from the bottom, at each time we have 4 strands, and they are divided to 2 pairs of 2 strands.
Looks like
Yes, let's make one more. Thank you very much. We can, and then we can, so it is like this, and this corresponds to the 4-point block or this rest-limited theory. And so here, this is described in terms of modular transformation of conformal blocks. We have 2 operators, so-called S and T. S is the modular transformation, and T is the half of the monodromy in the corresponding conformal field theory. And for example, this knot will be the following correlator. So we have T1, 2, T squared. Then we should change which strands are closed. So we apply S. Then we take T cubed. Then again S. Then T. And take matrix element of this. Matrix element of this between vector. So, and these S matrices are known as Raka matrices or 6G symbols. And the trick now, which allows to do a lot of knots, is to combine these 2 approaches. And we can actually not close this.
Исходная задача состоит в том, чтобы вычислить значение функции на конкретных узлах.
Yes, there are a lot of interesting properties that one can observe even experimentally and find some structure, algebraic structure among them. And there are very few known knots for non-trivial representations other than torus. So the trick is to unify these 2 approaches. We can actually not close this, but consider this as operator acting from some representation lambda times lambda or lambda bar to lambda times lambda. And then for any 2 subsequent strands here, we can introduce such 2-bridge configuration. A simple crossing would be just simple bridge like this. But this you can open and put in any configuration, in any break. And this way, almost all nodes can be done. And there are some nice facts which are very interesting, which are very easy to formulate, but for some of them I have no idea why they are true. And they are generalizations of ideas of Danforth, Zhukov, and Rasmussen. And the central object here is the following property. If we have H lambda colored complete polynomials, so they are polynomials in A and Q, where A is Q to N for the group S of N. There is this stabilization property, and then if we substitute H lambda for color, not polynomial 1 Q is equal to 1, and literally A. Then this is just the trivial polynomial when Q equals to 1, and the 2 the power which is now a number of boxes. And more generally, if we consider just expansion of this polynomial when Q is arbitrary, H lambda of any Q and A is this times expansion in, so Q is equal to exponent of H. So we have expansion in H bar. So we obtain some exponent here and sum over partition Q, H bar to some function delta E, and chi lambda Q. These are characters of symmetric groups. And this has many connections to Hurwitz theory, to topological recursion. And so these conjectures that I will tell later, they can be considered as nonlinear generalization of the Hurwitz theory.
Sorry, initially we were going to reduce H lambda as a polynomial with single.
Yes, but it depends on N, where a group is S1.
Yeah,
Yes, and it can be expressed as a polynomial in two variables, A and Q, where A is Q dot. This is a very beautiful result, but I forgot to mention that it stabilizes when N goes to infinity and is described by a single polynomial. Basically, because for generic N, representation theory is the same. For small diagrams, but the ways of Casimir operators between representation and dual representation can be different. The notion of dual is different because, for example, lambda k is dual to lambda n minus k. But if we don't introduce dual representations, then it's the same. And also this has some version for simple polynomials. So P lambda of Q, they depend on three variables, Q, T, and D. These are they conjecturally exist in many people studying them. But then,
what do you mean by these characters of symmetric groups? Normally, characters of irreducible representations are indicated by a single
exactly, but we evaluate character on certain conjugacy class. So mu is conjugacy class, and lambda is the representation.
So, lambda
Yes, of like C. Thank you very much. So conjecturally, there are some superpolynomials that generalize this, and Q and T are McDonald type variables. And when Q equals to T, we should recover just only the polynomial H lambda of Q and T. They are known and constructed for very few families of knots. I will mention later. But this property generalizes to the following for these superpolynomials. So if we take just symmetric representation at Q equals 1, then this is the single box of Q equals 1, A to R. And for the wedge representation, instead of Q, we should put T. Then we can consider, instead of Q goes to 1, we can consider what happens if A goes to 1. Such limit H lambda of Q and A is equal to 1 is known as Alexander polynomial. And the fact is that Alexander polynomial of Q in any representation this is equal to Alexander just single box of Q to lambda, where lambda is a single hook representation. So if the representation has just a single hook, then this is true. And it gets dramatically more difficult when it has more hooks than one. And also, let's see what happens when Q is not just 1, but a root of unity. Quantum groups, they behave always very interesting when Q is a root of unity. So Q to M is equal to 1. Then let's just start with symmetric representation. Then it is HSR times HSM is equal to HSR plus M. Any question? And they depend on A as functions of A.
Yeah, but there is a function R.
Yes, this is true for any R if Q to M is equal to 1. But also it is true if Q to 2R is equal to 1. Obviously. Yes, and if we have arbitrary representation lambda, then the following is true, that H lambda times H to representation Sm is equal to H mu, where mu is any diagram so that. So we have diagram lambda, and mu is obtained by adding a single hook, a single skew hook of length 1, single connected skew hook. So this it should be of length m, and this is diagram mu. These are our representations that appear in the following. We take Pm, the power sum symmetric functions, times Schur function S lambda. Then this is an alternating sum S mu times minus 1 to the height of this diagram lambda mu, mu lambda, minus 1. So we pick any mu from this formula, from this expansion, and for individual mu, this relation is true. But I can prove only some linear combination of these identities that involves all mu here in this expansion. And this is the Nakayama formula. Also, let's talk about Kashaev polynomial. Kashaev polynomial is the following. In representation lambda, here lambda is the complex polynomial of lambda when q is a primitive root of unity. So q squared is equal to e. Yes, q squared is e to pi over m and a. So instead of q, we substitute primitive root of unity. Then it turns out that k lambda of a is equal to k just levels of a to the power of lambda. And lambda also should be a single hook. And this is, if you compare this property of the Alexander polynomial and this property of Kashaev polynomial, they look very similar. And this is some mysterious AQ duality, which is totally unclear how to prove. Okay. Now, let's talk about the so-called differential expansion. This is some expansion that follows from some differentials introduced by Untitled and Rasmussen. And first, let me state is for this expansion for the figure 8 knot. This is a specific knot. Then, if we take symmetric complex polynomial for this knot, then we have the following expansion. It's 1 plus r times a over q, kq, plus a q binomial coefficient r2, a over q, a q, oh, sorry, it's going to be aqr, aqr, aqr plus 1, and so on. So it's like a binomial formula, some deformation of the binomial formula. When q is equal to 1, we know by the property of factorization that this should be just product, some power of the polynomial. But this is a deformation, and each term, the following is obtained in this very simple way. We consider the first contribution and the two factors as the two sources. Then they give two towers. They give a over q times a times aq and so on. And this gives you aqr, aqr plus 1, and so on. And what for general knot? The general knot, HR is equal to 1 plus sum s from 1 to r, also some sort of binomial expansion, rs, times some polynomials of n times, we have the factor corresponding the tower corresponding to the second factor, product j from 0 plus minus 1, and you are plus j. But instead of this tower, we don't have it, and we have a single factor a over q. For any s, there is a polynomial. The statement here is that gs are polynomials. This is a non-trivial statement. And they are much simpler usually than form the polynomials itself. And for any s, there is a knot for which gs is reducible. But if you consider, if you fix a knot and consider gs with increasing s, they become always reducible in a very regular fashion. Actually, this structure is parameterized by some number delta, which we call defect. For example, this is some integer number. For example, for delta equals 1, gs is divisible by the following. So this is aq, aq squared, and so on. And here we have 2, 3, 4, and so on. So each new s, if we increase s by 1, we get one more factor. If delta is equal to 1. If delta, for example, is equal to 2, then we have one new factor for each 2. Yes, exactly. So for yes, so this grows like s, this grows approximately like s over 2. And in general, this is s minus 1 over delta of integer part. So every node is parameterized, this structure for every node is parameterized by one single number delta. And delta is a very simple quantity, actually. It is the degree of the Alexander polynomial. This fact is totally unclear.
So that's
Yes. So for any node, delta for that node is the degree in Q of the Alexander polynomial. For example, here we have linearly growing factors, and it corresponds to delta equals 1. So degree of the Alexander polynomial is 1. And it follows from this that what is Gukov now investigating, that if we substitute a equals to q to some negative power k, and consider h as n for a for q minus k and q, this is a function of q. Then the coefficients of this stabilize when n goes to infinity. It follows from vanishing of large contributions for this expansion. So from this point of view, the simplest nodes are nodes with the smallest possible delta, where we have the largest number of factors, and the rest can be described sometimes very explicitly. And the simplest,
what other examples?
For example, any twist knot. So this is the knot which looks like this. Like very much like a torus knot, but we have this braiding instead of closure, tracy closure. So, and for twist knots, so we managed to define simple polynomials using this structure. and some more general notes actually.
To define or to
Both. And the definition is a very computable formula actually.
no, my question is different. Whether this phenomenon is defined for anyone.
No,
No.
no, it's a conjecture that it exists.
Yes. Since there is no definition, it's not
Yes. But if we define somehow for some nodes, we observe that it satisfies a lot of properties and dualities which are very hard to satisfy. That's why it's some fundamental structure. But let's first start with the formula for the polynomial for the figure 8 node in rectangular representation. It is the following. So if x is equal to q to r and y is equal to q to s. So we have Young diagram r times s. It is the simplest to state in rectangular representations. So then consider the following sum gives you complex polynomials. This sum over all Young diagrams and here product over boxes in the Young diagrams. Here the following factors x cubed is a prime minus l prime. I will explain this. Y cubed l prime minus l prime over u to r plus x plus 1 squared ax cubed l prime minus l prime a y inverse u l prime minus l prime. So it is a series where if we have a box, then this is called A prime, this is called L prime, this is A, and this is L. So A plus L plus 1 is the hook length of the box. So, and if we look at this formula, we observe a very important geometric meaning of it. It is a localization computation of the equivariant Euler characteristic of a certain shift on the Hilbert scheme. So Hilbert scheme of points in C2. This is space of ideals in C of in the polynomial ring of two variables, so that the quotient over I is finite dimensional in the dimension of this is equal to n. So we have non-natural torus action on this, which acts on the plane C2. The torus T1, T2. Then fixed points.
with respect to this action.
Yes. The fixed points for the Hilbert scheme are parameterized by monomial ideals. They are Young diagrams. And if we consider Young diagram, lambda, the tangent space of this Young diagram is sum over boxes C1 A plus 1 C2 minus L plus C1 minus A C2 L plus 1. So it is 2n dimensional space, and the character is this. And there is also canonical. There is a shift, the tautological shift U, whose fiber at I is finite dimensional rank n vector space Cxy modulo I. This is the space of functions on the corresponding subscheme in C2. And if we look at this formula, for example, we have in the denominator A plus 1 plus 1, it means that we take T1 equals to Q squared and T2 equals to Q minus 2. Action of this subtorus and localization formula is that the equivalent Euler characteristic of any shift, equivalent shift on a smooth variety X is equal to the equivalent Euler characteristic on the fixed subscheme of the following shift F times the co-normal bundle X over X on the fixed subscheme. So we have summation over fixed points, and the tangent space of the fixed point, if T1 and T2 are Q squared and Q minus 2, these terms are the same, and we have it in the denominator, as it should be. And it is the Euler characteristic of the following shift. We can, what we have in the numerator, QA prime minus L prime, it has to do with the shift U. And it is the following shift, Euler characteristic of some symmetrized wedge algebra. I will define it later, of X times U plus A U times lambda by inverse U plus A inverse U times K times the virtual canonical shift and the symmetric version of the exterior algebra is just usual exterior algebra times the determinant of representation in the power minus 1 up. So if we take this shift, then its equivalent characteristic on the Hilbert scheme is complex polynomial for this node in rectangular representation. So one shift parameterizes all complex and all rectangular representations. And this sum actually is finite because of the presence of these two terms. The sum is restricted to partitions which fit to the diagram R times S. So it's a summation over some diagrams.
Which were R and S?
Yeah, X and Y, they are related with R and S.
X and Y, and also the summation.
Summation over all diagrams, and diagrams which don't fit, they are automatically zero. So, and for torus nodes, so all twist nodes are parameterized by number m here, by number of twists here. And one value of m is just trivial, and all other are parameterized by non-zero integer numbers. And this node is the figure 8, and this, which is the reflection of it, is the trefoil, which is a torus node. And this duality for complex polynomials, it corresponds to introduce if we multiply this by just the tautological shift determinant of U minus 1. So a similar formula we obtain for the torus nodes. And to get simple polynomials, a natural generalization, a natural deformation of this is just to take arbitrary T1 and T2 instead of just the subtorus which preserves this symplectic form. So this defines super polynomials, and this torus node, this trefoil node, it is a torus node, so it belongs to another family of torus nodes. So its intersection with other important family of nodes, and for them, for torus nodes, there is other.
Here's a summation is taken cells and lambda.
Yes, exactly. Thank you very much. So for torus nodes, Чередник introduced super polynomials by totally different construction, which also has to do with Hilbert scheme, but in a very different way. So to start explanation about torus knots, let me give you a formula for just home field. For torus knot NM in any representation lambda. The formula is the following. We take the short polynomial corresponding to lambda and apply Adam's operation psi m. So psi m, this is operation on the space, on the space of symmetric functions, and it maps pk to pmk. So we apply this, and then we apply the following operator q to 2m over m times w2, and w2 is the so-called cut and join operator. And then we evaluate this at special point in pi is equal to bracket ai over qi. And w2 is the operator that acts diagonally in the Schur basis. And if we apply it to Schur polynomial S lambda, we get sum over cells in lambda, quantum of quantums. And this cell apply it to Schur polynomial. This is the explicit formula. It is called Rossa-Jones formula. And Чередник invited a deformation.
What is the first name?
Rossa. And Jones, a mathematician who just recently passed away. Anguri buffer is related, but in some other context of topological vertex. For example, if we consider Hopf link with lambda and mu, it corresponds to topological vertex with lambda and mu, and there you have Anguri buffer formulas. They count empty brains and so on. This is a formula, and what is the deformation that Чередник obtained using Daha algebra? But in modern language, it is better to do to deal with the Hilbert scheme, where we use symmetric functions as the key theory of the Hilbert scheme of points on C2. Then the formula is the following. We take the virtual structure shift as an element of the key theory, apply certain operator of the, I will explain later, and then take its pairing with the wedge algebra of AU. On the case theory of the Hilbert scheme of points on C2, there is action of the algebra UH bar of GL1 double Z. This is the quantum toroidal algebra. This is double created algebra. And we select slope n over m in this algebra. Then on this line, there is Heisenberg algebra of operators. So P lambda and m is the Macdonald polynomial for the slope n over n. So we select these generators as of the Heisenberg algebra SP as Newton polynomials, and write Macdonald polynomial of the operators, then apply it to the virtual structure shift and take a pairing with this shift. And then it turns out experimentally that for trefoil, for the only intersection of these two panels, you get the same answers whenever you can compute it. But this procedure is much harder to compute because you have to do with lambda times L boxes. So we have appearance of the Hilbert scheme in two ways for this superpolynomials, but the relation is not clear at all.
But numerically,
They agree.
that's agree.
Yes. There are also formulas of this kind for other twist nodes and more general diagrams with two parameters with some modifications of the shift. But there is nothing to compare with because they are defined only for torus. For the trefoil, it agrees numerically for all available representations. So, yes, I want to finish at this point, and if you have any questions, you are very welcome.
Yeah, thanks. To whom belongs this stability result? As an realism, then you obtain the sequence of.
Yes.
For a given representation, you obtain the.
No, what is N?
N is
For SLM.
of the group.
Okay.
And we have the same representations generated by Young diagram that we obtain polynomials that we.
Yes.
To whom belongs this result?
It follows from the Artin theorem. We can represent a knot as a closure of the braid, and in the braid all the strands are parallel. We don't have anti-parallel, so we don't have to deal with the dual representation. And our matrices are the same because they have universal Drinfeld formula for the R matrices. Yeah, it follows from this.
So you have the interpretation of this formula in terms of the kind of localization of
Yes.
some Hilbert problem, Hilbert scheme problem. Is there a direct correspondence without reference to some fixed points?
No, it would be very interesting to guess. But yes, for torus modes, it is more geometric. This procedure is more geometric because it can be interpreted as the action of some correspondence in the flat Hilbert scheme, and this correspondence, in some geometric way, corresponds to the knot. And then you can view all the relations in terms of Hilbert scheme of the flat Hilbert scheme. But for this, why we get twist knots and such description, it is completely mysterious.
Are there results about computation of invariants in all representations together, rather than some specific representation?
This parameterizes for all rectangular representations together. Yes, and for other representations, I can construct the shift by hand, but I don't have a general proposal for other Young diagrams. It seems that there is some procedure, but I can't formulate it.
More questions, comments? Okay, then let's thank the speaker.
Сейчас нет ли у нас вопросов?
Хорошо, спасибо.
Спасибо.